Hello friends, welcome to UGC EPG Pathshala. I am Dr. Jitendra Sarova, Associate Professor from Department of Geography of Dr. Bhimrao Ambedkar College, University of Delhi, Delhi. Today I am going to elaborate upon upper air circulation, jet streams, origin, types and distribution, which comes under the paper Climatology. First of all, let us discuss what could be the learning outcome of this module. While going through this module, you will be able to, number one, define upper air westerlies, Rossby waves and jet streams. Secondly, you will be able to explain the index cycle of jet streams. You will be able to explain the origin and characteristics of jet streams. You will be able to describe the types and distribution of jet streams. And finally, you will be able to highlight the significance of jet streams in determining surface weather conditions. One of our common observations is the movement or drift of clouds. This movement, sometimes fast and sometimes slow, indicates that upper air moves in upper troposphere also. Before World War II, upper air observations on scientific basis were very limited. Volcanic eruptions, balloons, aircrafts and satellite imageries have provided a great deal of data to prove the existence of upper air westerlies, Rossby waves and their high velocity core, that is jet streams. Jet streams play a significant role in determining the surface weather conditions, including latitudinal heat transfer, temperate cyclones and monsoon mechanism. In this module, our focus is on the understanding of upper air circulations and especially jet streams. Temperature, atmospheric pressure and air circulations are quite different in upper part of the troposphere as compared with those prevailing near the Earth's surface. The upper air circulations are predominantly geostrophic. Recall that pressure gradient force, which is always perpendicular to isobars, onsets motion of partial of air from high pressure area to low pressure area. You also have idea from previous modules on planetary pressure belts and general atmospheric circulation that as winds start blowing due to rotation of Earth, Coriolis force deflects it towards right hand side in the northern hemisphere and its magnitude is proportional to wind speed. Therefore, as the parcel of air accelerates, its deflection increases. Finally, a situation comes when wind turns so much that it starts blowing parallel to the isobars. This represents the situation of the geostrophic balance, that is, two opposing forces, pressure gradient force and Coriolis force, are exactly same. Therefore, the resultant winds are known as geostrophic winds, as is shown in figure number 1. In the middle and higher latitudes of both the hemispheres, upper air westerlies prevail due to balancing act of pressure gradient force and Coriolis force. It is well known that winds are result of pressure variations and speed is directly related to pressure gradient. The relationship between pressure and wind direction was first formulated as Bias-Ballett's law in 1857. It states that if you stand with your back to the wind in the northern hemisphere, your low pressure will be found to your left and high pressure to your right. You can verify this case of upper air westerlies in figure 2nd. Here, atmospheric pressure is low towards the pole and high towards the equator in the upper part. It is also noteworthy that in upper air, atmospheric pressure decreases towards poles. In upper part, pressure gradient increases with height. Therefore, wind's velocity increases with height, but this is generally limited to tropopause. Further, the balancing act of pressure gradient force and Coriolis force is resulting into the development of upper air westerlies. Poleward from the tropical headly circulations in both the hemispheres, air flow in the troposphere is normally and persistently west to east, generally parallel to latitudes as upper air westerlies. You can refer figure number 3 for this. The figure 3 shows 4 major elements of upper air conditions, namely A. Polar low, B. Persistence of upper air westerlies in the middle and higher latitudes, C. Tropical high pressure belt, which is constituted by a number of high pressure cells, and equatorial easterlies between equator and subtropical high pressure cells. The upper geostrophic winds are easterly. Similarly is the condition in the southern hemisphere. The uniform flow of upper air westerlies is frequently disturbed by the development of large scale undulations known as Rossby waves. The core part of the Rossby waves with steepest gradients and presence of maximum speed winds in narrow bands represents jet streams. Rossby waves and index cycle of jet streams is our next focus area. The Rossby waves develop along the narrow polar front zone of contact between two contrasting large bodies of air, cold air mass on the poleward side and warm air mass on the equator side, as is shown in figure number 4. These are called Rossby waves because they were discovered by scholar C.J. Rossby in 1937. The direct interaction between their core parts was experienced by pilots of B-29 jet planes of USA during the World War II. The wavelength of the Rossby waves is in the range of 2000 to 4000 kilometers on an average. Therefore, about 4 to 6 Rossby waves can be identified around circumpolar region at a time. These waves play a significant role in determining weather conditions of middle latitudes and are specially associated with genesis of temperate cyclones and anticyclones. The index cycle of jet streams represents the change from straight path to most sinus path of Rossby waves and jet streams. This transformation takes place in about 4 to 6 weeks and is normally divided into following 4 successive stages or phases. We will discuss these phases one by one. The first stage or phase, in this stage jet stream prevails near the pole and occupies a general east-west direction. It operates in polar front zone with the presence of cold air mass in the north and warm tropical air mass in south in the northern hemisphere without any undulations. The polar front is fairly smooth and stable, which means Rossby waves are absent and path of jet stream is straight, as is represented in figure number 5. The steep pressure gradient and consequent high velocity jet streams prevail west to east in this strongly established upper air westerly circulation. In this stage, surface planetary westerlies of mid and high latitudes are strong, zonal and located slightly poleward. This stage is known as the stage of high zonal index. The pressure systems are oriented as zonal, that is in east-west direction in particular latitudinal zone. The latitudinal heat exchange is limited and cyclonic activity is prevalent in high latitudes only. Let us come to the second stage. In this stage, the straight path of jet stream changes to undulating or wavy path, which means Rossby waves begin to develop. With the passage of time, the amplitude of the jet stream increases and it starts shifting gradually towards equator. The minor undulations deepen gradually. The cold air makes inroads towards the equator and warm air towards high latitudes. Let us come to the third stage. In this stage, the path of jet stream becomes meandering and its amplitude registers significant increase. Rossby waves and jet stream moves towards equator and operate up to 20-degree latitudes. The pressure gradient, which was equatorward to poleward in previous two stages, becomes west to east in this stage. And large-scale latitudinal heat exchanges occur due to the movement of cold air masses towards equator and warm air masses towards poles. The cold air makes inroads into lower latitudes in deep embayments which emerge as troughs of low pressure at high levels. Two such troughs of low pressure are clearly visible in the third diagram of figure 5th. Correspondingly, high pressure ridges are created by the intrusion of tropical warm air in embayments between the troughs. This stage is associated with outbreak of temperate cyclones or wave cyclones near the surface, as can be seen in figure number 6. Let us come to final fourth stage. In this stage of jet stream index, the meanders are at peak and the amplitude of the Rossby waves increases so intensely that large pools of warm tropical air cut off and isolated in mid and higher latitudes, and likewise large masses of cold air are trapped in lower latitudes. Instead of east-west circulation or zonal, the north-south or meridional circulation predominate. This is why this stage is also known as low zonal index stage. Many circulation patterns emerge which follow cyclonic pattern in low pressure areas or upper troughs and anticyclonic circulation in high pressure ridges represented in the diagram respectively by symbols L and H in figures number 5th, 6th and 7th. In this stage of low zonal index, north-south contrast of weather conditions and wind speed are minimum. The pressure systems and frontal systems are oriented in meridional position. Therefore, zonal character of upper level westerlies gets fragmented into a number of shells. It is noteworthy that in this final stage, the detached masses of cold air become cut off lows, which are cyclones in the upper troposphere. Likewise, warm air embayments also get detached to form cut-off highs as upper air anticyclones. These cut-offs process helps in latitudinal heat transfer and plays a vital role in maintaining global heat balance. This cut-off process takes place many days for completion. This transfer of or redistribution of heat eventually reduces the thermal gradient and upper air flow becomes flatter and surface weather conditions stabilize. The Rossby waves are formed gradually and it is not necessary that they will move up to the cut-off stage. They may remain stationary for long periods and may dissolve without approaching the cut-off stage. The atmospheric stability and instability are greatly linked with Rossby waves and jet streams, troughs and ridges. All the four stages of index of jet streams, that is development of Rossby waves, to their dissipation are shown in figure 8 with special reference to North America. On the basis of understanding of 4 stages, Rossby waves and index of jet streams, it can be concluded that wavy flow in upper air is associated with surface weather patterns. During the phase of relatively flat or small amplitude waves, the stability prevails and cyclonic activities on surface are very limited. Conversely, when the aloft air flow manifests large amplitude or curved path having shorter wavelengths, atmospheric instability prevails and is reflected in cyclonic disturbances. Let us come to jet streams, their definition and characteristics. Associated with the Rossby waves is a narrow band of very strong winds known as jet streams. Jet streams are found in mid-latitude upper troposphere, usually blowing west to east, that is as westerlies. These winds attain their highest velocities at 10 to 12 km altitude. The wind velocity is highest at the center and decreases outwards towards its peripheral parts, as can be seen in figure number 9. This way, it resembles a stream of water moving in a water container. In this figure number 9, the cross section of the jet stream shows circular isotachs over western United States. Isotachs are line joining places of equal wind velocity. The core at the height of about 11 km has the strongest winds at 150 knots or about 300 km per hour. According to scholar Nemias, a jet stream is essentially circumpolar in character, which meanders and completely girdles the earth as upper air westerly in both the hemispheres. Generally, jet streams are thousands of kilometers in length, about 150 to 500 km wide and a few kilometers thick vertically. Wind speed in jet stream is on an average about 140 km per hour. They move at an average speed of 110 km per hour in summer and about 190 km per hour in winter. But occasionally, the wind velocities may be about 450 km per hour or slightly more. Over Northern America, wind velocity on an average in a cross section of jet stream is about 60 km per hour in summer and it all around doubles to about 125 km per hour in winter. The vertical shear of wind, that is the gradient of wind velocity with height, is of the order of 5 to 10 meter per second per kilometer. The lateral or horizontal wind shear is about 5 meter per second per 100 kilometer. An arbitrary limit on lower side for wind speed along the axis of a jet stream is 30 meter per second. The highest velocities of jet streams are observed in its core region. Generally, as the jet moves from over an ocean to over a continent, its velocity increases due to steeper pressure gradient over land. Conversely, while moving from continent to over an ocean, the velocity normally decreases. Jet streams are characterized by great seasonal shift in positions. With the change in overhead position of sun, the jet streams shift poleward in summer and equatorward in winter, as can be seen in the figure 10. In winter, the pressure gradients are steep due to intense thermal contrasts and consequently wind velocity is higher in winter, about 2 times that of summer season. Jet streams follow meandering path. In summer season, the crests or ridges of the Rossby waves are located over the continents and the troughs over the oceans. In winter, the continents are under the troughs of the wave while the oceans are under the crests. The seasonal northward and southward shifting is also more conspicuous over the continents than over the oceans. This is mainly due to the differential rates of heating of land and sea. Let us come to the origin of jet streams. The origin of winds and its velocity are function of pressure differences, which are result of temperature variations. In case of polar jet stream, this temperature variation is result of contrasting cold air mass on polar side and warm air mass on equatorial side of the polar front zone. As cold air is dense and compact than warm air, air pressure decreases at a faster rate in colder air mass as compared to warm air mass or column of air. It means that north of the polar front zone there is a higher pressure as compared to its south at one particular altitude. You can refer figure 11. As a principle, temperature falls more rapidly in a warm column of air with altitude and pressure falls more rapidly in a column of cold air with altitude. Thus, the fall in pressure with altitude is higher in case of areas of low temperature. Therefore, the fall of pressure north of polar front is steeper than towards its south. In such a situation, an isobaric surface, that is equal pressure plane in atmosphere, will be sloping towards areas of high pressure on ground. Also, the isobaric surfaces of the successively lower pressure will become steeper with higher altitudes, as can be seen in figure 12. Over the tropical region, as temperatures are higher, air pressure decreases more gradually than over the cold polar areas. Consequently, at same altitude above the surface, higher pressure prevails over the tropics and lower pressure over the polar areas. Therefore, the resulting pressure gradient is directed towards areas of high pressure, that is tropics, towards the areas of low pressure, that is polar areas. Thus, thermal contrast at surface results into steep pressure gradient in upper air. The intensity of the thermal contrast is at peak during winter season. Therefore, the pressure gradient and resultant jet streams are strongest during winter, as can be seen in figure 13. Due to pressure gradient force, air motion should be from tropics to poleward as indicated by red arrow in figure 14. But the Coriolis force also comes into play and counterbalances the pressure gradient force. Therefore, jet streams as a geostrophic wind moves from west to east as upper air westerly. The key aspect of origin of jet stream is large thermal contrast at surface which produces steep pressure gradients aloft. Hence, stronger upper air winds as jet streams within the slower general westerly flow or as core of Rossby waves develops. Let us come to types and distribution of jet streams. On the basis of their location or distribution, jet streams are classified into following types: polar jet stream, subtropical jet stream, easterly tropical jet stream, stratospheric subpolar jet stream, and finally local or regional jet streams. Let us discuss them one by one. First, polar jet stream. It is also known as polar front jet stream because it is associated with polar front. Polar fronts are linear zones which occur due to large thermal gradient created by convergence of contrasting cold air mass of polar areas and warm or mild air mass of tropical areas. It occurs near tropopause between polar cell and feral cell, as can be seen in figure number 15. They are most active at 300 millibar, that is at altitude of about 9 km within 40 degree to 60 degree latitudes. The seasonal shifting is in the range of 30 degree to 70 degree latitudes in both the hemispheres. Second is subtropical jet stream. It is also known as subtropical westerly jet stream. It occupies a position at the tropopause between Hadley cell and feral cell at the altitudinal range of 9 to 13 km, as can be seen in figure number 15 and 16. In case of this jet stream, the front of contrasting air masses is not present and surface thermal gradient is also very poor. Its origin is related to a thermal gradient confined to upper tropopause. In comparison to polar front jet stream, it is much more persistent. Third one is easterly tropical jet stream. It forms in the upper troposphere over India and Africa in summer monsoon season only due to regional reversal of north-south thermal gradient. They are associated with intense heating of Tibetan plateau during monsoon season. The tropical easterly jet stream is limited to summer season and northern hemisphere only. This jet stream occupies position at very high altitude, that is about 15 km. It is located over the Hadley cell, as can be seen in figure number 17. It plays a significant role in monsoon mechanism. The extent of monsoon season in Southeast Asia is associated with its presence. Fourth one is stratospheric subpolar jet stream. These are also known as polar night jet streams. They originate in stratosphere at an altitude of about 30 km around the poles in winter season, as can be seen in figure 18. Finally, local or regional jet streams. Over the period of time, due to better data acquisition techniques, scholars have identified many local or regional jet streams of temporary nature. For instance, Somali jet stream, which can be seen in figure 19. They originate due to local level thermal contrasts and dynamic changes in upper troposphere. These have significance in influencing local weather conditions. Let us now come to the significance of jet streams. Although weather scientists are not yet fully aware about the origin, forms and features of different types of jet streams, yet they have been able to establish relationship of jet stream with many surface weather phenomena. The most well understood and well established relationship is between jet streams and mid-latitude temperate cyclones in the belt of westerlies. The troughs and ridges of Rossby waves and jet streams are associated with cyclonic and anticyclonic conditions in the upper air as well as on surface. Temperate cyclones and associated precipitation is above normal whenever upper air jet streams are positioned over cyclones. The index cycle of jet streams results into latitudinal heat transfer between tropics and mid latitudes and plays a significant role in global heat balances. Jet streams play a very significant role in monsoon mechanism. The onset of monsoon is directly associated with northward shifting of subtropical westerly jet stream. Subtropical jet stream occupies position over the Great Plains of India in winter season. Till the time jet stream prevails over this area, it maintains a pressure gradient from north to south and this is not in favor of onset of southwest monsoon over India. Therefore, the shifting of subtropical jet stream north of Himalayas is prerequisite for the establishment of Hadley cell over Indian subcontinent. In summer season, the temporary tropical easterly jet stream also plays significant role in monsoon mechanism because it tends to strengthen the summer monsoon. Subsiding air on its left margin creates a high pressure over the Bay of Bengal and the Indian Ocean, while rising air under its right margin causes low pressure under its right margin over the Great Plains region. Therefore, it helps in enhancing the south to north pressure gradient steeper. Hence, it is associated with the strength and length or duration of southwest monsoon season. Subtropical westerly jet streams bring western disturbances in northwest India during winter season. This results in precipitation in North India during winter season. Jet streams also play an important role in the movement of air masses and associated weather changes in the trajectory. Thus, it is well established that jet streams play a significant role in surface weather phenomena. Let us come to the summary and conclusions. Temperature, atmospheric pressure and air circulations are quite different in upper part of troposphere as compared with those prevailing near the Earth's surface. In middle and higher latitudes of both the hemispheres, upper air westerlies prevail due to balancing act of pressure gradient force and Coriolis force. The uniform flow of upper air westerlies is frequently disturbed by the development of large-scale undulations known as Rossby waves. The core part of Rossby waves with steepest gradients and presence of maximum speed winds in narrow bands represents jet streams. The index cycle of jet streams represents the change from straight path to most sinus path of Rossby waves and jet streams. This transformation takes place in about 4 to 6 weeks and is normally divided into 4 successive stages or phases. In jet stream, wind velocity is highest at the center and decreases towards its peripheral parts. This way, it resembles a stream of water moving in a water container. Generally, as the jet moves from over an area of ocean to over a continental area, its velocity increases due to steeper pressure gradient over land. Conversely, while moving from continental to over an ocean, the velocity normally decreases. Jet streams are characterized by great seasonal shift in positions on the basis of their location or distribution and influence of weather conditions. 3 main jet streams are polar jet stream, number 1. Second is subtropical jet stream, and third is seasonal easterly tropical jet stream. Although weather scientists are not yet fully aware about the origin, forms and features of different types of jet streams, yet they have been able to establish relationship of jet streams with many surface weather phenomena. The most well understood and well established relationship is between jet streams and mid latitude temperate cyclones in the belt of westerlies. The index cycle of jet streams results into latitudinal heat transfer between tropics and mid latitudes and therefore plays a significant role in maintaining global heat balance. Jet streams, both subtropical westerly as well as easterly, play a very significant role in monsoon mechanism. Jet streams also play an important role in the movement of air masses and associated weather changes in the trajectory. Thus, it is well established that upper air circulations play a significant role in surface weather phenomena. Thank you very much.